So today I'll be talking a little bit about some of the research me and my lab have been working on towards programmable social robots for everyone. When you attend conferences, read about journals, you typically see socially assisted robots being discussed a lot. You might see this in THRI or IJSR, and they're being deployed. These social robots are actually being deployed in a variety of settings, ranging from healthcare to education to the service industry. And it's expected to kind of transform services all over the world. And at least that's what they say a lot in these journals and conferences. And usually they're looking at supporting healthcare professionals or educational professionals in delivering some sort of service, such as autism therapy. So on the bottom right here, you can see our lab developing a robot for delivering an autism therapy to children with autism. In the bottom left, it's one of the older robots I used during my PhD called Brian at University of Toronto. There we were trying to deliver some cognitive therapies. It's a skin-like robot. You'd think it's a little bit scary, but actually older adults kind of like it. I'm actually really surprised about that. And then everybody probably knows Pero, which is more for like pet therapy. Our lab has been also deploying this in for physical therapy exercises for older adults, and supporting activities of daily living in long-term care facilities. And then looking at that, they're also exploring how we can augment the existing workforce. So not just delivering services that people are already doing, but actually how can we make these healthcare workforce more have better capabilities, for data collection. So can the robot detect, what is the children are learning, where they might be falling behind, and then actually adapting their behavior to actually support the healthcare professional in the delivery of the service and making these services a little bit better. Also analyzing these complex data sets that you might not have available to you. If you're a healthcare professional, you're just kind of observing things and then marking it down. If you have a robot, you can actually systematically do that, and then it can provide you some support in that way. And then also, we've been exploring, how one healthcare professional might be able to actually utilize maybe multiple robots to serve more children simultaneously or more older adults simultaneously, again, augmenting their capacity to do more work. And then finally, people are obviously exploring the expansion of those capabilities beyond what's possible right now. So, people in the military might be deployed overseas. They might have to bring their families to a location where you might not have autism therapy. You can't get access to a therapist. And if you do remote therapy, it's like some sort of crazy time that you don't have access to. So you might develop a robot to actually deploy that overseas with some individual families. And so they can maintain their services and still receive that treatment that they desire. Also, providing in-home care is another thing that is pretty difficult long-term and really expensive. So there's a lot of exploration for older socially assisted robots to be deployed in the home for preventative care or providing some sort of support for activities of daily living for people with cognitive impairments or intellectual and developmental disabilities, so that they don't have to go to a group home or a long-term care facility and kind of maintain that independent living. So I've been working in this field approximately for over a decade, maybe 2 decades now, I'm not even entirely sure. But I've been seeing that there's been a significant progress being made, with AI and robotics and bringing it closer to these domains. But we really have yet to readily see them outside of lab settings or very, very controlled studies to a certain extent. And, I'm often also deploying those robots in these facilities and seeing what the real world impact is. And when you're talking to these actual stakeholders, these actual end users after a HRI study or a focus group or some participatory design that we do, a core concern are two things, really. Robots are single-use tools, and so it's really hard to adapt those. What healthcare professionals see is like, it's really hard to adapt a robot to the vast needs that you'd expect maybe a child with autism needs, because you're constantly trying to improve as or delivering new interventions as a child improves their capacity. And also that makes it really hard to decide on like the cost benefit of actually even like deploying the robot. It's a lot of effort to deploy it, learn the technology, and actually use it. So often these healthcare professionals are a little bit conservative about like the actual deployment of it. And then there's also a lot of technology anxiety towards how complex these systems are actually to use and perceived by the general population. So a lot of people are still really hesitant on deploying actual robots in these more, let's say, I would say high risk scenarios with children or healthcare. And so really my career over the last while has really focused on understanding how we can enable non-technical experts to teach and customize specifically social robots to the individual needs of the stakeholders, whether it's the individual child or the patient or the healthcare professional that is supporting these individuals. And we've been exploring this in 4 specific different ways. First, identifying approaches where we can transfer knowledge from a non-technical expert to a robot so that it can autonomously deliver or perform a task. So what's the best way to actually transfer this knowledge? How does somebody envision themselves teaching these robots this task? And then investigating how these robots now can actually learn from the data that's being produced, as well as trying to improve upon the teacher's actual knowledge. And then how can we actually make these robot models and as well as what the robot learns explainable as well as transparent to these non-technical experts, but also domain experts so that they can actually repair misconceptions the robot may learn or some gaps in knowledge that it doesn't have. And then finally, we actually deploy this pretty frequently into these actual facilities, these actual domains, and we kind of are looking to see how we can actually train these non-technical experts how to utilize these technologies in practice. So kind of towards this goal, I first started with exploring how we could use learning from demonstration techniques that were typically utilized in physical robotic interactions to social robotics in the social robotics domain. And there's a long-standing history of using learning from demonstration in physical robotics. But one of the challenges with social interactions is the state space as well as the action space is a lot less constrained. You're not constrained in what you can do in the physical environment around you. You can kind of say anything, you can interact with people in a variety of different ways. So it is a little bit less constrained, and so it's a little bit of different learning process. And this kind of brought me to one of my first projects focusing on using AI a long time ago to acquire knowledge from healthcare professionals in long-term care facilities to actually train social robots for tasks that they may need the robot to do. And specifically, I had these healthcare professionals co-create these multi-user group activities, specifically for cognitive interventions for older adults in these long-term care or residential care facilities in Canada. And so the system, our goal was primarily make it easy to use, make it easy to teach, and try to extract as much knowledge as we can from the actual human, at least from what I thought was easy to use at that time. And the healthcare professionals ended up creating some trivia games and bingo games and actually deploying it in their facilities. So what this kind of teaching process initially looked like was you teach these primitive robot behaviors, so individual social behaviors, so you'd have to break down the task into these social behaviors, and then show the robot when you should apply these social behaviors, so look at the state of the actual social interaction, or potentially some game state, and then it would learn some policy to determine in the next given state what action should I actually take, and then it would be deployed on a robot, actually delivering some of these activities to a group of older. From that study, we found that these healthcare professionals to a certain extent could teach these robots some tasks. I found it relatively easy to use. many commented on the usefulness of being able to actually customize these robot behaviors because the specific needs of their actual facility and the need to do that. And we actually deployed this and had the robot, after they learned the task, interact with 30 older adults. Obviously, they enjoyed it because the healthcare professionals knew exactly what the older adults enjoyed. So they had engaging experiences with it. But with all that said, during that study, there's lots of challenges that healthcare professionals had in actually designing the robot-mediated therapies, utilizing the actual learning from demonstration system. There's two primary things. First, it's really hard for non-technical experts to understand what the capabilities of a robot actually are. So even though you say, oh, you just kind of like, it can say things and move and see particular things, it's very hard for them to understand what can the actual robot do. And so they didn't understand where it would best fit. And then the second thing is, even if the healthcare professionals knew where the robot might be able to fit, they they couldn't really formulate a good mental model on how they should actually teach this robot, because it often didn't really match how they expected how a human would be taught. And this is because the approach that I was showing there was, you do need a little bit of computational thinking. You have to break down this task into its individual elements and then find out in a given moment what you should do, and then also simultaneously make sure that you cover the whole entire space of possibilities of interactions that you would have. So it's very easy for a healthcare professional to actually miss that. So, I started exploring, and our lab started exploring, looking at different ways in how we can improve that transfer of knowledge from a domain expert, like a healthcare professional or educational expert, into that actual robot. So actually acquiring better demonstrations from them. And this kind of led to our first investigation of using these VR-based interfaces, which was inspired by the concept of homuncular flexibility. So basically, if a person is placed into a different embodiment, they can actually acquire the capacity and adapt to that body and perform particular tasks. So, this is very clear in people who actually lose an arm and they're able to perform a new task. But let's say if you gave somebody a tail, over time they could probably figure out how they could use this tail to pick up something. We were especially interested in this for social human-robot interactions because it's often very unconscious how you socially behave. So a lot of the movements you do and all the gestures you do are kind of unconscious. So often when we're actually designing some of these interventions with healthcare professionals or educational professionals, you tell them, oh yeah, how should the robot move? And they're like, I don't move my body. And then you record them performing the actual task and oh, do a lot of movement, and that's what it makes it engagement. The robot can't just stand there and not not actually move its body, or else it's really, really awkward. So we basically use that concept and we immerse the users in the body of the robot and immerse them into basically the sensory capability. So you can only hear and see what the robot would be able to hear and see. So you can't cheat to actually perform the task, because you would have to use what the robot has access to. And then you can only use the way the robot body can move. So you can actually see how it would move and how you should actually demonstrate so that the actual agent could learn correctly. And so this is where I moved towards therapies for autism spectrum disorder, I was deploying this and actually developing these interventions manually, but also I was trying to explore how we could actually teach robots, and so we kind of combined this together because autism therapies usually have almost thousands of different therapies that are customized to a particular child, and so you always have to be adapting to the child and creating new interventions. So if a robot is to be deployed in these settings, which is frequently being deployed, you'll have to actually adapt to what the child needs at any given moment. So taking those two things together, we ran a study and conducted a study to kind of seek and investigate whether virtual reality-based interface where you immerse somebody in the capacities of the robot would support them in better transferring their knowledge to a robot, but also what is the most effective modality for them to actually be able to design these robot-mediated therapies. And later you'll see kind of them adapting their body to actually how the robot embodiment is, and how like the limitations of what it's actually able to replicate, because the robot has like less degrees of freedom. And then the second question we were kind of answering here was whether therapists could actually independently design a robot-mediated intervention and actually operate the robot. So we compared that VR-based interface to a kinesthetic teaching-based interface. So this is the VR-based teleoperation interface. So you can see somebody's wearing an HTC Vive. There's two screens and you can see it one from each eye, and so you get some sort of stereo vision. And then if you move your arms, the robot moves its arms in a particular way. But if you see like the actual users putting their hand not exactly where the robot's hands are, so you actually have to adapt how you actually show your demonstrations to the robot. And then that kinesthetic interface uses some sort of block-based programming, which is a little bit more similar to what I did previously. And basically, you would have to create these individual robot behaviors using kinesthetic teaching and keyframing the motions of the actual robot. And then they would just create that trajectory for the actual robot. And then the scripted robot behaviors could be executed in using a graphical user interface during an intervention. Which again contrasts our VR-based teleoperation interface for delivering an intervention, because you usually require a little bit more computational thinking, and you don't just move your body and intuitively deliver the therapy. So we conducted a user study to actually deliver or to investigate these research questions with a group of therapists at an autism clinic. And really their goal and what they were asked to do was deliver this emotion recognition intervention to the children with autism. So basically teaching them how to recognize particular emotions using the robot. And this was actually during the pandemic, so it's kind of great because like they didn't ever have to interact with the child, so they could actually deliver that therapy through teleoperation. And so each therapist really went through an experimental procedure where the first day they delivered the actual intervention with their own physical body. Then on the second day, they were trained to use the two systems. So they got a little bit of time to practice. It was about like 30 minutes because it's really hard to get therapists time. And then on the third day, they actually delivered the intervention to a child. And we're collecting data on intervention planning and design time, but more importantly, treatment integrity. So like, are they following the procedures necessary for a effective applied behavior analysis therapy, and as all they implementing the different components correctly using the actual interfaces. And then there was the intervention times, as well as their perceptions of usability and workload towards those interfaces. So this is kind of a video of what that looks like when somebody is using a VR interface. And again, you'll see that she is actually adapting her body to be able to actually produce emotions on the robot, because the robot's like appendages are like shorter than hers, and she's taller than it, and so like it functions a little bit differently.
How do I feel? Good job. How do I feel? Let's try again. How do I feel? Angry. Awesome. Dog says.
So these are actual ABA intervention techniques, and it looks a little bit awkward when you're doing it with an adult, but that's just envision it with a 2 to 3 year old child or 2 to 8 year old child. And this is the block-based kinesthetic interface that they were using. So basically what she's doing is first she creates this block, and then it represents the actual behavior for the robot. And then she starts keyframing different poses, and then creates the trajectory of how the robot should move. And then second, so this is like one specific pose. She touches the head, which saves its position. And then that's one frame, and then she does it again, moves the head, touches the top of the head, that saves another frame, and basically that creates a trajectory. And then she adds a block to express the speech the robot should say in this particular case. So you should drag something here, type some stuff. And then combines it all together to create, like, generate a full interaction. So Connor, if you end up using this, there's choreograph if you want. Quick tutorial. oops, sorry. But anyway, the more interesting thing is here, she's actually interacting, or another therapist is actually interacting with a real child. The child is behind the screen just for HIPAA and privacy, but it's from the perspective of the robot.
How do I feel? All right, done. How do I feel? Happy. Nice job. How do I feel? Yeah, good job.
So overall, therapists were able to independently design and implement these robot-mediated interventions to deliver to a child with ASD. They had really positive perceptions towards the VR interface in comparison to that kinesthetic-based interface, and they actually performed on par with what they would do with their own physical body. And so we actually analyzed that, and we had actual expert director of the clinic make sure these therapies are delivered correctly. And therapists also found the VR interface much more natural and adaptive to the children, obviously, because they could kind of interact in real time. But then we took that data, which wasn't that too much data, but we took that therapist data we collected from that previous study, and we basically attempted to learn a interaction from these demonstrations. So basically, we tried to fuse together the challenge previously we had of taking these taking a high level task and being able to segment it into these low level behaviors. And so the user no longer has to do that, and the model would be responsible for it. And basically, we used this really basic convolutional neural network with the spectrogram, and we tried to train a LSTM based model to actually have the robot predict what's the next appropriate given action for the robot, given the actual child response.
How do I feel? Sad. Let's try again. How do I feel? Angry.
So that's a great video and all, but there's a variety of challenges with actually utilizing that technique, because for learning from demonstration, like for specifically that a convolutional neural network based approach, it requires quite a bit of data, and demonstrations, you can only get so many demonstrations from actual human before they get tired of actually interacting with you. And the other thing is that these data sets are really imbalanced. So you might be able to observe a therapist on a good day or a bad day, and you might find that they only behave in one particular type of interaction. So when you're collecting these data sets, you actually are missing a very large part of both the state space and the action space. And so in our case, the children were mostly answering correctly on that day when we were actually collecting data. And so they didn't really need prompts for them learning some emotions. And so as a result of that, when we actually tried to deploy this in reality, it was very difficult for the model to be able to generalize. Also, the black box nature of these deep neural networks is that it makes it really impossible to repair without just giving it more data. And so we wanted to look for more interpretable solutions, especially given the constraints of actually deploying this in practice, because our assumption is that you'd have very little data. And so we want to be data efficient, and also making sure that when we deploy the model, we're sure that it'll behave correctly when it's interacting with a child. Because in these particular cases, we don't want to deploy a model and find out, oh, it's teaching the child the wrong thing, because we care about children. And there's a lot more risk early in their lives. So we began exploring both more interpretable as well as explainable and data efficient techniques. Current machine learning approaches in specifically social learning from demonstration focus on teaching a single task usually, generally require a significant amount of data. So if you look at a lot of the papers, they use actually a ton of data to actually train the model and really lack any form of explainability. So we developed a method specifically for learning multiple forms of autism therapy interactions, and really the goal was, again, being both data efficient and transparent so that somebody could actually repair the learned representation. So kind of leveraging what we learned from our prior study, we elected to use, again, this Wizard of Oz style restricted perception approach for a teaching interface. We took off the headset because it's kind of a pain to wear. For those of you that have worn them, you probably know. We made sure to restrict that perception because it was giving us better quality data and also still ensured that the therapist knew how the robot would move, how it would behave after you have taught it. So you basically get a good sense of the robot's capacities. And then algorithmically, instead of having users actually define these, again, individual actions the robot could utilize in the therapy, we automatically segmented these actions. The nice thing about ABA therapy is it's relatively structured to a certain extent. So you have a stimuli the demonstrator was using to teach a child. You have these prompts for actually supporting a child to respond correctly. You have rewards for them answering correctly, and then error corrections for incorrect answers. So to perform these actual action segmentations, we collected a bunch of trajectories of like key joint positions of as somebody is delivering the therapy. And then we also collected their utterances, and anytime there was some sort of activity, whether it was gestural activity or verbal activity, we would just segment that as a quote unquote action to be used in the subsequent steps. So here we then clustered leveraged the actual structure of ABA therapies, and we would cluster individual actions into behaviors. So a behavior really refers to this higher level concept of grouping for individual actions. And so, for example, let's say you have something like praise. You can praise somebody in many ways, like great job, you're doing great, or something of that nature. And you can also wave in many different ways. So we're trying to cluster those different actions together into a single behavior that is related to each other. And then we also clustered these behaviors into skills that a therapist is actually trying to teach the actual robot. And so after segmenting, we actually learn a policy where the robot is able to look at the historic behavior history between a child and a therapist, and we actually match that behavior history back to the current child action, and then it determines what the next robot behavior should be. And if there's like multiple potential candidate actions or behaviors the robot should take, we basically have some sort of k-nearest neighbor approach that determines what's the closest actual child observed previous child action that matched the observed child action. And the reason for all of this is just really to make the algorithm more transparent to somebody actually deploying this model and seeing what it's actually learning. So this is what our interface kind of looked like and kind of the approach that one of my students, PhD students have developed for that. Sorry.
What's those signs? What doing those signs? Oh my.
So this is it posing some candidate actions, and then it's kind of semi-supervised here.
Here's the interface for explaining the robot decisions. On the left, you can see the action. On the right, you can see the action that the robot has proposed. And on the bottom, you can see the similar action from the history that the robot uses to rationalize its choice. Here is the cluster repair interface. On the leftmost column, you can see the list of learned skills. In the center column is the list of behaviors for a given skill, in this case, touch head imitation. And on the right, we have the action editor, where an individual action can be reassigned to a new skill and behavior.
So we conducted experiments again with a variety of participants. They were asked to more, in this case, simulate children's responses. And really, we were evaluating the system on its semi-autonomous capability to actually propose the correct actions. So we made it semi-autonomous so that'd be a ground truth to compare against. So if the controller decided that this wasn't the correct action, basically the policy failed in that particular case. And what we found was the skill clustering accuracy was relatively high, 99.5%, and really the only error was actually a human error. And then the behavior clustering accuracy was about 75.8%. And these errors were mostly related to, again, verbal praise, where verbal praise is very similar across the different behaviors, whether you're trying to teach a child to touch their head or recognize a particular emotion. So the sentence embedding weren't different enough to be assigned to the different clusters. And there was also some speech to text errors as a consequence of some of the systems that we were using. But what's more important from this, and really the takeaway really was that by repairing these errors and making the actual the system transparent to an actual teacher, is that we could almost improve the policy accuracy or the ability of the system to perform correctly in a given interaction by about 10%. And so it actually greatly increased the accuracy of the policy by allowing this repair with very little data and demonstrations. So that prior technique that we developed really enables people to customize or customize a robot for these autism therapies, but we're actually making a pretty strong underlying assumption that we're teaching an autism therapy which has a very distinct structure. And so more recently, we've been exploring the benefits of things like interactive task learning, which should be relatively intuitive to non-experts because it's very conversational. You're basically explaining to the robot what to do and giving it some sort of underlying structure to learn on. And then it also allows the robot to kind of interactively ask for clarifications on what it actually is learning and explain its own understanding of what it's actually gathering. And it naturally grounds the teaching interaction in language. So it's basically more interpretable, natural, and efficient. And so just to recap, interactive task learning has two really important components. The first is the teacher describes the task to the actual robot, and the robot can ask for clarifications if necessary. So here we have in the purple text what is the robot, and basically the robot's asking, what should I do after a person approaches me? And here we're trying to teach it how to be a hotel concierge. The teacher then lets the robot know you should say, hi, my name is Alpha, how can I help you as that hotel concierge? And the robot can further probe for information. Okay, what should I do next? Is it a sequential kind of decision that you're trying to do, or a sequential series of actions you're going to do, or should I just branch into a different state? And then the learning of the task is actually grounded in the dialogue. So hypothetically, it should increase interpretability, naturalness, and learning efficiency. And as you can see still here in the diagram, there's a lot of back and forth dialogue. The robot can again provide a clear explanation of what it understands according to the teacher's prior dialogue. So, the robot says, after I say, hi, my name is Alpha, what should I do? So basically it clarifies, this is what I heard, this is what I should do. And again, interactive task learning it has been used a lot in physical manipulation robots. It hasn't really been used too much in social robotics, again, because of the grounding, without the grounding in the physical environment. So we need a lot more robust language understanding. This is pre-ChatGPT, but we were using a lot of the large language models out there. And basically, my student Alex developed a model a technique that models the actual learned task as a behavior tree, something visually easy to understand for somebody. It learns reusable procedures to build these subtrees, and then uses a transformer-based large language model to actually parse a wide variety of commands. So here's a diagram of that system architecture. Basically, there's an input utterance from the actual teacher, and the instruction is then put into a KNN classifier to determine if it's one of 6 different intents. The most important thing here we're looking for is actually whether it's an instruction intent, which then goes to our instruction parsing system, where we mask out quotes. Basically, we use the BERT language model to actually mask out quotes of what the robot should say, or what the hotel guests will potentially say. And then we actually use this T5 parser that we trained to actually create this parse of the actual functional components of the actual instruction. And then you remap that back on the actual quotes so that you can actually parameterize these different commands the robot is actually learning. And you'll also use like this GPTJ rephraser, because when you're teaching someone, usually you say something like, ask the hotel guest what they need. But you actually have to have the robot learn that from the first person perspective, which is actually asking the person what they actually need. So you actually have to rephrase it into that first person perspective. And then the learning agent is basically there to basically go back and forth and have this active learning where you clarify statements, ask for more information, or ask if it's like just the end of what you're trying to teach the robot. And then we conducted, again, experiments where we compared this to these learning from demonstration techniques, where we had the robot be taught either from using our interactive task learning or learning from demonstration. So you just show the robot what to do, like we did earlier. And the robot was taught, specifically the fur hat robot was taught to be a hotel concierge and to accomplish 6 subtasks that we told them to actually teach the robot. And we measured things like performance, trust, and workload. And so this is kind of what that interaction looks like, or these 2 different interactions look like.
What should I do after I say, "Hi, I'm Alpha, how can I help you?" If the person wants to check in, tell them, "I cannot provide you with a road key. I have no hands. My friend Brian on the left can help you check in." "Hi, I'm Alpha, how can I help you?"
Hi, I'd like to check in, please.
"I can't provide you with a room key, but my friend Brian can help you with check-in." "Hi, I'm Alpha. How can I help you?" "I'd like to check in." "I cannot provide, but my friend Brian on the left can help you check in."
So this is her just testing the model after it's being trained. Unfortunately, there was actually no difference between those 2 techniques when we looked at it from like the performance standpoint and the perception standpoint. But actually, when we're looking at like what the participants were actually saying qualitatively, there's different benefits and drawbacks for each technique. So looking at some of the open-ended questions, participants really found like they had a lot of control, or they felt like they had a lot of control, and there was a lot of transparency when there was the interactive task learning, but it wasn't really as intuitive as you would have expected just by explaining how to perform the task. And this is because, again, it's a little bit difficult to for people to understand things that you do not need to teach a robot, because your assumption, a lot of at least people with a lot of computer program experience feels like they have to like teach every single little aspect to the robot, so they get into these infinite loops of this is what yellow means, and like it's a pixel that is like this particular color, and so they get really deep into the teaching interaction, and you can't really pull them out of it. Also, users also were often tried to teach the things that the robot already knew, and also things that it can't actually learn. And then some groups of individuals actually think about things just purely sequentially. So we told them to teach them 6 subtasks where you adapt based on what the sorry, not patient, but customer needs are. But what they ended up doing is teaching one task, and once the interaction started, they just taught all 6 tasks. So you're teaching somebody how to check in, greet, and then also having it also give suggestions for restaurants, even though the customer didn't even ask for those things. So maybe with more training, we could have got the participants to perform better. We actually didn't really train them very much. We just tried to see how intuitive it could be for them to actually utilize. Among those challenges from that study, there's really 3 core things we've been seeing. People have a poor mental model of the robot. So we kind of are trying to right now investigate how people actually think about when they're teaching a robotic system, and like also whether different factors from their background affect that, things like computer programming experience or potentially like their style of teaching. There's also participants who misjudged the robot's common sense and prior knowledge. So we are looking at ways to also have the robot be able to communicate and break out of those infinite loops of, you don't need to teach me this, I understand it already. And also one of the other things is trying to get participants out of if they're not able to produce the conditional logic, can the robot actually be able to identify there is an issue here? Can I actually repair the actual model and know that I'm learning the wrong thing, or there's a little bit of uncertainty in what it's learning. So right now we're exploring a variety of areas. Again, we're increasing the common sense knowledge and self-knowledge of the robot. So can it figure out, again, if it's having issues? We're also exploring these visual interfaces to make the learning more transparent to the user. Hopefully that gets into Roman and people can see that. And we're also looking at better phrasing in this interactive task learning, because honestly, choosing specific phrases in the interaction vastly affects how people will teach that robot and what they will say to it. And we're also considering now fusing learning from demonstration and interactive task learning, so we can get both the structure and actually the demonstration, which is a more natural type of teaching mechanism for most people, or at least that's what we are currently think. And I'd like to thank a lot of these funders, the National Science Foundation, DoD, as well as NSERC, which is Canadian. Yay! Of course, I love my wonderful lab for all the hard work that they do, and the wonderful PhD students out there.
All right,
Thank you.
So